So today we're going to do again two lectures. So this morning we will mostly focus on adversarial examples in machine learning, and then this afternoon we will see how to cope with them using a cryptographic techniques called differential privacy. So I call that second part of the session of today, differential privacy for adversarial robustness. So these are the main topics. I will first start with a basic recap of machine learning, in particular neural networks, just to see that we are all on the same page with this, but probably you will already know many of the things that I'm going to say about that. Then we will move to adversarial examples in machine learning, specifically in deep neural networks. And then this afternoon we will see first differential privacy in general, and then how to apply it for adversarial robustness. Here I put some references that you can look into to have to dust off your knowledge of machine learning or to build it up if you don't have it. So the first one is actually a very nice book. It's quite old, book by Thomas Mitchell, Machine Learning, from 1997, and it's also freely available online. So this is nice to give rigorous and comprehensive introduction to machine learning, not only in the neural networks case. Also the book by Dave McKay is also nice, that is like the connection between information theory and machine learning. And that is also quite old, but it's also freely available online. And then I found this book, the third one by James and others, that I didn't read in detail, but skimming through it seems quite nice, and it has the advantage that it is much newer. It is by second edition is from a couple of years ago, and it's also freely available online. So you can also find it on the web page of the authors. And then we will have some papers scattered through the slides as references for the specific contributions on adversarial learning, adversarial examples, and differential privacy. So let's start with a recap of machine learning. So the definition that I usually like about machine learning is the one that comes exactly from the book by Tom Mitchell. So the one that I was showing in the previous slide. So basically we say that if we have a computer program, an algorithm, then we say that it learns from a certain experience E with respect to some task to solve T, and some performance measure that is saying how good is the program in solving that particular task T. If this performance on the task T is improving with respect to this measure P with the experience E that the program is accumulating. So this is the most encompassing definition of a machine learning algorithm in general. Then we can have a lot of types of machine learning algorithms. Mostly we will focus on what are called artificial neural networks, and we can single out, let's say, three basic components of this kind of machine learning algorithm. So the first one is a model or a computational model that is actually implementing the program to, let's say, to solve the task T that we defined in the first slide. And the model, for example, in our case, will be mostly artificial neural networks, as I said. Then we have typically what is called the loss function. That is the measure of performance P. So it is measuring how far we are from recognizing, let's say, a particular distribution of sample with our computer program, with our machine learning algorithm. And then we have an optimization procedure that is able to minimize this loss function or this empirical error. We have different types of machine learning in the sense that we can have supervised learning. So in supervised learning, we have basically a set of training examples that are already labeled by a human teacher in a certain sense, and they are used to train the algorithm. In unsupervised learning, instead, we don't have this setting of the training set, and usually this is the realm of, for example, clustering algorithms, where a machine learning algorithm is finding regularities in a set of or patterns in a set of data. Then we have hybrid situations with semi-supervised learning, and also reinforcement learning, which is another breed that we won't see into this in this course in particular. So supervised learning. let's start from there. So we have, like I said, a training set that is composed by pairs. So pairs are, let's say, composed by the first part, the first coordinate, x, that is, let's say, the input that we want to give to our machine learning algorithm to classify typically. And y instead is the intended output that needs to correspond to that particular input. So these pairs are called training examples. X is also called a feature vector because usually it is itself a vector and each component is called a feature. This is just a machine learning lingo, let's say. And y instead is called, the output is called the level also. So how do we level that particular feature vector? And the objective is to find a function that is able to interpolate, not only, let's say, it is able to interpolate the training example, so we always have y that is equal to f of x for each possible training examples. In general, what we hope for is that since we cannot train the machine learning algorithm on the whole possible set of instances, what we hope is that this machine learning algorithm, once it has been trained over the training set, is also able to generalize over unseen instances that are not contained in the training set. So in particular, to test this part, to gauge this part of the generalization, we test the trained model F after it has been trained on the training set over what is called the test set. So, okay, it's a little bit quirky. In supervised learning, we can have different type of classification depending on the type of label. So if y is a real number, then we have what is usually called regression. Otherwise, if it is a Boolean variable, it's binary classification. Either some input belongs to some concept or it doesn't belong to that concept. So it is basically concept learning in the sense of learning a particular subset from the space of instances. And if y is also a member of a finite set, then we talk about multi-class classification. So for example, if we want to classify animals with respect to their names, to their species or whatever. And the learning method usually is based on what is called the empirical risk minimization. So we have a set of parameters of our machine learning models that are denoted by theta. And then we want to solve this minimization problem. So basically we want to minimize over all possible combinations of parameters the sum of the loss function, so the function that is measuring how good our machine learning model is doing with respect to the training set, basically. And we sum this over all possible training examples, so from 1 up to n. Okay, now here is a model of machine learning algorithm that we are going to see a bit more in detail into this lecture, and it is called the multi-layer perceptron. So first, before going into the multi-layer perceptron, let us define or recall what are neural networks in general. So neural networks. We start by defining what is an artificial neuron. So an artificial neuron is basically a unit like this. So we have here our neuron here, and then we have some other inputs for these neurons coming from here. So 1, 2, etc. So we have input x1, x2, up to xn. So this neuron is taking n arguments in input. Each input is not fed into this artificial neuron like in as is, but it is weighted with some weight. So each input has a weight associated. So W1, W2, up until Wn. And then what does the neuron do? It computes a weighted sum of these inputs. So we will have basically the sum for I that goes from 1 up to n of the multiplication of the weight, Wi, by the input xi. So it's basically a scalar product, a linear operation. Are we done with this? No, because usually, beside having this, that is a linear operation, artificial neurons also have the so-called threshold. And this is, let's say, an analogy from neuroscience, because biological neurons usually don't fire just after computing a linear combination of the synapses that are connected to them, but they are firing only if they reach a particular threshold value. And here, threshold values can be a lot of things. I'm putting this symbol here that will be clear in a moment. And then this will be the output of the neuron. So what we have basically is, let's say, the whole artificial neuron that is composed by a function, let's call it act, of this linear combination. So sum from I that goes from 1 to n of wi by xi. And the activation functions can be many. Usually, like historically especially, artificial neurons were studied with what is called the Heaviside function, so hs of x, which is defined as simply hs of x is a piecewise constant function that is 0 if x is smaller than 0, and 1 if x is greater than or equal to 0. So I put this symbol here because it is exactly the graph of this function. If you plot this function, you will have like, you will have here until 0, you will have 0, and then there will be a sharp step here, and then you will have 1. So this would be x and Heaviside of x. Okay, this is one of the possible activation functions. Otherwise, we have the sine function as the n of x, which is basically the same thing as Heaviside, instead with the difference that instead of having 0 here, we will have -1. So we are just really taking the sign of the argument x. And then there are other activation functions that we will see later. For example, the logistic function, that is this one. So let's call it, well, log is not a, let's just put the algebraic expression that would be 1 over 1 plus e to the minus x. So this would have instead a shape like this, like it's more of a sigmoid. And this is actually good, we will see later, because it is differentiable. These, like the sine and the Heaviside function, are not differentiable because you have a sharp discontinuity. And the fact that it is differentiable is useful for the matters of learning, let's say. So what does it mean to learn in a neural network? So this neural network is basically computing this function, okay? And we want to be able to say, for example, if we have the Heaviside function, to do like a Boolean classification of a particular concept, or to learn a particular Boolean function, basically, because we have either 0 or 1 as a possible output. So learning basically means to find the correct set of weights here. So this is mostly what learning is about in neural networks. And the classic way of training this kind of neurons, that are also called the perceptrons in the literature. So perceptrons. It's something like this. So we start, so let's call it classic training. We start with random weights okay, so in the beginning this will be just random numbers, and then we start by, let's say, seeing with our training, with each training example that we are feeding into this artificial neuron, what is the outcome, and in particular if it is correct or not. Okay, so basically what we want to do after we have computed, let's say, for a single training example, the corresponding output, is to measure the error and then to update the weights iteratively. And then we continue like this for each subsequent training example. So we will do an update of all our weights. So for all weights Wi, we will have something like this. Wi will be Wi again, plus an error delta Wi, which is in particular equal to this delta Wi. So eta of t minus o by x I. So basically here we are saying that the error will be composed by what? Would be the target or the level of our example, so the correct level, minus the output of our of the neuron, let's say. And then we will also have this eta, which is a small constant called the learning rate that is able to control the step with which we are converging towards the correct function that the neurons need to learn. What is the problem with this? So basically we are doing this iteratively for each training example in the training set, we said. The problem of this is that it works only if the training set is defining a function which is called linearly separable. And what does it mean to be linearly separable? Well, basically it means that you can find an hyperplane in the space of instance which is able to separate the two classes. So those that are, let's say, belonging to the concept, to the Boolean concept that we are trying to learn, and those that do not belong to this concept. So in particular, if we do a very stupid example with Boolean functions, let's say that we want to learn the Boolean function end. So we have something like 0, 1, 0, 1. And the end of 2 bits will be 0, 0, 0, 1. So we say 1 only if we have both inputs x and y equal to 1. So if we represent them over the Cartesian plane, we could say something like, here we say 0 because both x and y are 0. Here we have 0 again because we have this that is 1, but this that is 0. Here we have again 0, okay, because we have 1 over y but 0 over x. And here finally we say 1 because both coordinates are equal to 1. Well, in this case you can see that these are all possible training examples that we can give to this very simple function. And basically we can find an hyperplane, in this case a line, that is able to separate these two classes. So those where we have 1 from those where we have 0. What happens? So this is called linearly separable. What happens, for example, if we choose to learn with this classic training rule, the XOR instead? The problem with the XOR is that it is not linearly separable because we have 0 here, 1 here, 1 here, and 0 here. So if we do it again here on this plot, we will have 0 here, 1 here, 1 here and 0 here. Now you can see that you cannot find a line or equivalently an hyperplane that is able to separate these two classes of zeros and ones. Why? Well, because basically they are crossing each other. So you should do something, find, let's say, a surface like this, for example. But this is clearly a nonlinear separating surface, so it's not an hyperplane. So this is the problem with the classic training rule. And another better rule to learn also the functions that are not linearly separable is called the delta rule. So the delta rule basically is able to converge to the best fit approximation of the function, even if it is not linearly separable. And how does it work? Well, basically we have a different way of measuring the error. So instead of just measuring it like by doing the differences between the target value and the output of the artificial neuron, then we have error function for our vector of weights, EW. There is, for example, something like this. So there are many others, but let's keep this. There is the simplest one. So D minus OD. So here we are again computing over all possible training examples. So D in the training set big D. The difference between the target value for that particular training example minus the output of the artificial neuron squared, and then we divide it by 2. Why we do this kind of error measure? Well, basically, if you plot it, for example, over a 3-dimensional, if you have only, let's say 2 possible dimensions in your classification space, you want to compute the error by plotting the surface of this function that is like in 2 dimensions, in 2 variables. So you will have something like here you have like x and y again, and this will be your error. Okay, so here you will have a surface, and if you use this particular error measure, then you will have a parabolic surface. So something like, okay, I'm very bad at drawing, but just imagine that this is parabolic surface in 3 dimensions. So since it is a parabolic surface, well, it's quite easy to converge to the minimum of this function here. So this point here, for example, this will minimize the error, and thus also it will provide the best possible approximation of the function that we are trying to learn with our perceptron. And the fact is that, as you see here, we are considering this function that is differentiable, but with a particular caveat, a particular trick. Here we are considering the artificial neuron without the threshold function. So it is just the part of the linear combination of the weights. Or we can consider it also with an activation function, but with an activation function that is differentiable. Otherwise, we cannot have like a nice shape like this in the error plot. So this is all good. Only thing is that basically this is still not satisfying, like using a single neuron, because using a single neuron you have like let's say a very incomplete representation of what you can do with artificial neural networks. So this is the reason why we move to multi-layer perceptrons. So in multi-layer perceptrons, instead of having a single artificial neuron, we have many of them, and they are arranged in layers. So you see here on the slides, you have an input layer, and then you have like a set of, or let's say a sequence of hidden layers, and finally you have an output layer. So each layer is connected to the next one, in a feed-forward fashion. So it means that we have only connections between neurons from one layer with neurons to the next layer, and we don't have any feedback or we don't have any side connection in the same layer. This is because otherwise this becomes like a dynamical system if you also have feedback, so it becomes what is called a recurrent network, and then you have other things to consider. So here it's very simple. We are just propagating the input, so the training example from the input layer, then we compute it with the one or more hidden layers, and then we have finally the output layers that will be the label for that particular input example. So the idea is that with hidden layers, we can have, let's say, a complete representation of all possible functions. In particular, there is a theorem that is called the universal approximation theorem, which basically tells you that if you have, it is sufficient to have a single hidden layer in this model here of multi-layer perceptron, basically approximate any function over a compact set to any desired degree of precision by having sufficient training examples, basically. So we can have just one hidden layers, but then in practice, what happens is to have like multi-layer perceptrons that are so-called deep. So we have deep neural networks in the sense that we have a lot of hidden layers between, because they notice that they just simply work better in practice than just having a single hidden layer and then trying to use the universal approximation theorem, because in that case you need to have like a lot of training examples. And in this case, the training is a bit more complicated. So the learning algorithm, it is still based on something like this, which was called the delta rule. Only thing is that we need to do it for each neuron. And how it is done, I'm not showing you the details, but the idea is to use what is called the backpropagation algorithm. And with the backpropagation algorithm, the idea is that we start from the input layer and we propagate the input of a training example. We compute the corresponding output in the output layer, and then we compute the error on the output layer using this delta rule. And from there, we propagate back this error using the chain rule, that comes from calculus, basically, to update also the errors of the hidden layers. And then we continue like this in a backward manner until we have updated all weights. And then we do it again in an iterative way to basically to do to finish the whole training set. Okay, so yeah. Okay, so this is for multi-layer perceptrons, and in general, I showed you here like this particular delta rule to compute the error. There are other, let's say, error measures or loss function. One common loss function that is used nowadays in deep learning, and that we will also mention later in other examples, is the cross entropy. So cross entropy is basically starting from the idea that you have two probability distributions, let's say two discrete probability distributions P and Q, okay? And then you compute the what is called the cross entropy, which is basically this formula. So H of P and Q, that is minus the sum over all possible points in our space of events, X, of the probability of X with respect to the distribution P by the logarithm in base 2 of Q of X. So what does it mean, this particular formula? Well, intuitively, it tells you what is the average number of bits that are needed to encode something coming from the distribution P when we are using instead Q as a model. So in a certain sense, it is measuring, let's say, how far these two distributions are. There is a small caveat here to, if you look into books of information theory, you will see that this is called cross entropy. Sorry, if you look into deep learning papers or deep learning books, you will see that this is called cross entropy. Actually, if you look into information theory books, you see that cross entropy is something slightly different. It's what is called the Kalbeck-Leibler divergence. That is basically the same thing, only that here you don't have the logarithm of this, but you have the logarithm of the fraction between P of x and Q of x. It's just a matter of terminology. I don't know why people in machine learning actually call this cross entropy, although it's not exactly the same thing. The Kalbeck-Leibler divergence is the same as this one, except that in the intuitive interpretation, it tells you what is the average number of extra bits that you need in order to encode something coming from the distribution P when you're using the model from the distribution Q. So this is quite commonly used in deep learning as a loss function. Basically, you have the distribution of your real concept or training concept that is represented by your training example, and then you have the distribution learned by your neural network at that moment, and you try to minimize this cross entropy. So to go further, we have also another model of neural networks that are called convolutional neural networks. These are quite popular nowadays. The idea here is that we still have, let's say, a feed-forward architecture, like in the multi-layer perceptron case, but each layer can be either of two types. Let's say, well, we have the initial input layer, then we have the hidden layers again, and then we have output layers. So that is similar. But each layer can be either a convolutional layer, like this one, or a pooling layer, which we will see in the next slide. So in the convolutional layer, basically we are representing our input as a vector or a matrix, and then we compute a so-called convolution with some fixed kernel that is linear. What does it mean? It means that we have this small kernel, for example, there on the slide that is 3 by 3, and we applied over the first 3 by 3 region of our input that is represented over a matrix. And then we shift it one place to the right, and we apply the same kernel. And then we shift it again, and we do it until we have passed the whole input value, the whole input matrix with this kernel. So basically, this is a shift invariant function, so you can think of it also as a kind of cellular automaton in a certain sense, because you are applying the particular local rule that is represented by the linear kernel over that particular neighborhood of the input matrix. So this is for the convolutional layer, and then we will have an output that will be something to put in the same pixel, in the corresponding pixel or component of our matrix. I'm saying pixels here because, of course, these convolutional neural networks are used a lot for image recognition. And beside convolutional neural networks, we have also the pooling layers, like I was saying. So in the pooling layer, we divide our input matrix or our feature map, also called like that, into regions that are non-overlapping. And then in each of these non-overlapping regions, we compute either the maximum value inside this region or the average. So it depends. You can have max pool or average pool, depends on the model. So here you have an example with this 4x4 feature map. We divide them like in 2x2 squares. And then in each of them, we are taking the maximum. So in the first one, we will have 21. In the second one, we will have 13, etc. So this is kind of distilling, let's say, the feature map in something smaller. And finally, we have the activation functions that we already talked about. So we have a lot of them. It could be either the identity function that is not doing anything, or we can have the binary step, which is the Heaviside function, or the logistic that we saw here, or the sign, or we can have also what is called the softmax the softmax activation function that is basically saying, okay, instead of giving a definite value for a label, I'm computing a distribution of probability over all possible labels, and then I'm returning what is the argument, so the label with the highest possible probability. So this is the idea of the activation function softmax. And okay, so the first block is done. Do you have any questions so far? Everything good? Okay, also on the chat. Okay. So now, after this basic and very quick recap of how machine learning and neural networks work, we start with something that interests us more in particular, because it has to do with security and cryptography in general. So adversarial examples in machine learning. So what is the idea? The idea is that once you train a deep neural network, or any neural network for that sake, like we said, after applying this backpropagation algorithm, the function is, let's say, learning a decision surface that can be nonlinear. So it is linear if we are like in the simple perceptron case, and we are, let's say, trying to learn something that is linearly separable. In general, we will have a decision surface that says, okay, this belongs to this concept, or this doesn't belong to this concept in the feature space. But the decision surface won't be a hyperplane, it would be something more complicated. So what is the idea of adversarial example? The idea is exactly to exploit this fact of the decision surface. So if you add to a valid example, to something that should be classified correctly, for example, as a panda by a neural network, you add enough perturbation, enough random noise, then you will mess up the classification of the neural network. And for example, it will say, okay, even if this to us perceptually, from the perceptual point of view, still looks like a panda, the neural network will classify it as a gibbon, for example. And what is the idea? The idea is that if you apply enough noise, of course, you will always move your point in the feature space from one side of the decision surface beyond it to the other side, and you will mess up the classification of the network. What we want to do, or what they observed in particular with deep neural networks, is that this perturbation can be very small, can be minimal, up to the point that you arrive to modify a single pixel, for example, like we will see in the following slide, and you are able to mess up the classification of a neural network from panda to gibbon, for example. So what is the meaning of these adversarial examples? So basically, you can think of them as this particular intersection in this set. So you have the space of real images, those that haven't been tampered by an adversary that is trying to craft up an adversarial example, and the space of images that perceptually to us look like real, so to humans they look like real. And then you have the space of all possible input images in general, and something that is classified with a wrong classes. So something that should be classified as a panda, for example, but instead is classified as a gibbon. So basically the adversarial example live over that particular intersection of these three sets. And why do they exist? Well, the fact is that there exist both robust and non-robust features, which means that, so the features, like we said, are the components, let's say, of the vector that is representing or encoding our training examples or examples to classify in general. And we can, let's say, divide them into robust and non-robust features. If you, let's say, compute or try to train your neural network using non-robust features, then basically what you get is a non-robust deep neural networks where it is quite easy to find adversarial examples. And in general, when you see in machine learning papers the accuracy measure of a particular neural network, this refers to the standard accuracy that is without considering robust features. On the other hand, robust accuracy is something that refers to accuracy also on adversarial examples. So if you train over robust features, basically you will have also a robust accuracy, and you will have a deep neural network that is able to, let's say, not be easily fooled by an adversarial example. Of course, like we said, if you apply enough noise, in the end, you will always mess up the classification of a neural network. But at that point, basically a human could also say, okay, this noise is enough for me to understand that something has gone wrong here. Someone tried to tamper with the image and try to craft an adversarial example. So this is for robust and non-robust accuracy. And like we said, non-robust features are enough for standard classifications. And as you can see here, for example, if you are saying with robust features, with non-robust features, you are classifying the training image as a dog. If you craft an adversarial example, then with the non-robust feature, you will end up, for example, with the classification of a dog as a cat instead. On the other hand, if you use a robust features for the training, then you will have a dog again, even if the original training image has been modified with an adversarial example that is small enough. Okay, now let's say that, like, if you remember from the first lecture, we said that in general we have like an adversary, like for example Eve in cryptography, that is able to break into a crypto system, and we wanted to model her capabilities in a certain sense, her capabilities, her goals, and the information that she had at her disposal to break the crypto system. Here we are considering an adversary from a similar point of view, but it is more the point of view of cybersecurity, where you use the so-called threat models. So you try to model an adversary with respect to the kind of threat that is posing to the system that you're trying to protect. So in our case, the system will be a deep neural network, and the adversary is someone who is trying to craft up an adversarial example. And threat modeling, usually you can find it like defined in many ways in cybersecurity books, but let's say that an encompassing diagram is something like this. So you first define what is the threat, the relevant threat that you're trying to protect from. And after you define, let's say, this threat, you identify specific components of these threats, like, for example, how difficult it is to carry out an attack with this particular hypothesis and stuff like similar to that. And then you come up with mitigation countermeasures and you validate them over the system. And after that, you go back to the beginning, because of course an adversary is in the real world is an adaptive adversary. So it will adapt to a particular countermeasure that you are applying in order to protect your system. And then from there you need to redefine, or let's say refine, your threat model. Now in our case, so now we are doing some threat modeling for adversarial examples in particular. Let's say that in the ideal case where we don't have any adversary, the pipeline of the machine learning algorithm of a deep neural network looks like a bit like this. So we have our data source on the left, and this data source is giving us raw data. So it is generating some data that we want to classify with the neural network. And we apply some measurement tool to extract from this raw data the so-called features. So to compose our training set, basically. These measurements tools usually are not perfect, so they will always be affected by stochastic noise in general. And this will mean that we have some errors in how we are also encoding our features to be fed to the learning algorithm. After that, let's say that the features are fed to the learning algorithm to learn of the model, for example, the decision surface of a neural network. And then finally, we will have our classifier that will be using the learned model from the learning algorithm. So here we are assuming, anyway, the important thing in the ideal case is that we are assuming that the noise affecting the measurements is stochastic. So it is just random noise and there is no, let's say, intention behind it. On the other hand, in the adversarial model, we have an adversary that is modifying both the noise So the noise is not anymore stochastic, but it's like intentional in the sense that the adversary is trying to modify what is measured by the measurement tools from the raw data in order to modify the features in a malicious way. And also he could, let's say, act over the data source itself in a certain sense. So this is, for example, if you consider the domain of automotive, for example, when you have like autonomous driving in particular, you have a camera on your car and it is like seeing at that moment a particular road sign, for example, stop. And it has been shown, for example, that by modifying the data source, so by modifying the road sign in that case, by putting, for example, a sticker over the road sign, then you are able to fool up the classification of what is seen by the camera and the neural network behind it. And so instead of interpreting it as a stop sign, it could be, I don't know, something like speed limit 120 kilometers per hour or something very dangerous like that. So the fact is that the adversarial model here that we are trying to consider can be both affecting the data source and the measurement tools with the noise that is not anymore stochastic. So this is an example of attack surface in different domains or concrete domains. So we already said automotive and computer vision. So we will have the physical domain, that is the road sign, and then the digital representation of the road data, that would be a JPEG picture of that road sign. Then after that, we will have some pre-processing, having like, let's say, a matrix of numbers, let's say, that are specifying the intensities of the pixels, basically. Then we apply the model. From there, we will have, let's say, for example, a softmax activation function that tells us the probabilities of the various class. And then from there, we take the maximum probability and we say, from there, we act back, we do a feedback on the real world. And for example, we engage the car brakes. In general, for example, you could also have another example with network intrusion detection systems. So in that case, you will have network traffic as raw data, and from there you extract these, network traffic as data source. From there you get the raw data that would be TCP dump, for example, dump of TCP packets. And then you reprocess them and extract the features and get, for example, the packet headers or metadata like that. And then from there you apply the model and you say, okay, the packets that I'm seeing are, let's say, for example, representative of possible malicious behavior. So someone is trying to intrude my network or not. If so, then you take some action, like, for example, you shut down a part of your network infrastructure. And in general, okay, you have the generic machine learning system that is following always this kind of attack surface model. So for characterizing the adversary in our threat model, we have to consider, similarly to the adversarial model in cryptography, what is the goal of the adversary, what is his knowledge, so what kind of information he has at his disposal, and what are his capabilities, in particular in terms of computational resources. So for the goal, in our case, since we are considering adversarial examples, the general goal is to mess up the classification of a neural network. It can be of two possible types. So the first type is targeted adversarial examples, where we say that we want to misclassify, to provoke a misclassification in the neural network to a specific class. So for example, I say I have an image of a panda and I want to classify it as a dog, for example. In the non-targeted goal, instead, we are happy enough if we are able to say, okay, we have the image of a panda. We are happy enough if we are able to misclassify it with anything else other than panda. For the knowledge that the adversary has, there are several components that he can know about the neural network that he's trying to attack. So it could be the network structure, so the architecture, like if we have a multi-layer perceptron or a convolutional neural network and so on. the type of activation functions that we are using, the hyperparameters that we are using to train our network. So, for example, the number of epochs that we are using for optimizing the loss function, etc. The training data. We could also know what is the training set, and so on. So we have a lot of possible combinations of these components that can be known by the adversary or not. The most extreme ones are the white box model, where basically the adversary knows everything, which is not very realistic, of course, because in general, the adversary in a real world scenario won't have all available information about the network. And then the weakest one, which is the black box model. So basically the adversary knows nothing about the network. And what he can do is just to query the network in a black box way. So we submit like an image, for example, or an input example, and he observes what is the corresponding output. So this is the black box model. And then we can have something gray box in between white and black box. Finally, for the capabilities, the attacker usually, well, it can modify both the training and the test set. In general, here what we consider in this setting of adversarial example is that the attacker can modify only the test setting, because modifying the training data is something that goes into the domain of what are called the poisoning attacks that we are not seeing here in this course. Also because it is quite difficult to counteract poisoning attacks, and in particular, as far as I know, there are no cryptographic techniques to counteract poisoning attacks. So here we are considering attacks where the adversary is modifying the test set. So after we have trained our model with the training set, then we modify by submitting, for example, fake inputs to our network. And then the attacker, the adversary, can do either a one-time attack, so we just have one query at his disposal to fool the neural network, or he can do it like in an iterative way. So he has several queries, or he can do as many queries as he wants. And so he can also adapt with respect to what he observes from the outputs of the network. Okay, so for the adversarial examples, let's say that we also need to consider some constraints. Like we said, if we apply enough noise, we will always misclassify what the neural network is trying to accomplish. But the problem is that adversarial examples should be minimal, should be very small and stealthy. So in particular, invisible to the human eye. And how do we specify in a formal way this constraint of small and stealthy? Well, we employ metrics over, let's say, distance over metric spaces. In particular, a common distance that is employed in machine learning papers is the Minkowski distance, which we already touched upon yesterday when we talked about the optimization of orthogonal arrays. Is the LP distance in substantially. So you will have that distance that actually is induced by what is called a norm. So you're seeing your feature space as your input space as a normed space with a norm, and this norm is inducing like a metric over this space. And the norm in particular of a single vector inside this space is given by this sum of all the components of the vector in their absolute value, exponentiated by exponent p. And then you take like the pth root of this sum. So basically, if you see the possible shapes of the balls inside this normed space, they changes with respect to the size, to the magnitude of p. For example, we start from something that is, let's say, the ball of radius 1 is not even convex when we have exponent p that is smaller than 1. Then it becomes convex if p is equal to 1, and in that case we have the so-called Manhattan distance. If p is equal to 2, we have the classic Euclidean distance, and then we continue until you get like, if you take the exponent p that is tending to infinity, at that point you have the so-called Chebyshev distance, where you are taking just the maximum of that particular sum. So this basically changes the shapes from that part there that was like a non-convex diamond to a square. And this will be used to, let's say, specify if we have a single example in our space, and we are using, I don't know, the Euclidean distance. So we want to specify the range of our perturbation in terms of balls with this, under this particular metric, under this particular distance. So we will say that we can accept as stealthy and small enough all examples that can be obtained by modifying something inside the ball of radius r. So this is the basic idea of adversarial examples that needs to be minimal. Okay, so now we move to the last part of the lectures, that is about using evolutionary algorithms to craft these adversarial examples. So first of all, we need to define a bit more what is the goal of the evasion attack. So we call an evasion attack an attack that is trying to construct an adversarial example that is able to fool a neural network. So we can consider it again as an optimization problem. And in this optimization problem, basically we want to minimize the distance between the original input x and the adversarial example x prime. And this must be, let's say, in such a way that the value of the function learned by the neural network over the adversarial example is a label L prime, and the value of the neural network over the original example is another label L, and these two labels, L and L prime, must be different because we want to cause a misclassification. And eta is basically the difference between the original and the adversarial example. So basically it is the perturbation. And we want this eta to be basically something that is inside a specified ball. Now, there are a lot of evasion attacks out there in the literature that can be, let's say, classified with respect to whether we have white box attacks or black box attacks, what we were saying before about the adversarial knowledge. And mostly what we will focus now are black box attacks based on heuristic search, so in particular on evolutionary algorithms. So that bottom right item. So here you can see like a historical timeline of evasion attacks in the literature. They started in 2013 with a seminal paper by Szegedy and others that was called like Intriguing Properties of Neural Networks, where they used a particular optimization algorithm called LBFGS that is performing line search. And they showed how to mess up the classification of a deep neural network that was classifying images. The problem was that, it was, of course, a seminal paper, so it was in the beginning of all this research thread. The assumptions were not very realistic because they were assuming a white box model. So basically the adversary knew everything about the structure of the network. Then we had other kind of evasion attacks. What we are focusing here now is this one pixel attack that you see here on the bottom in 2017 by Su and others. And the idea of the one pixel attack is that we are going to modify just one pixel in our image. So this should be, let's say, small and stealthy enough with respect to our requirements. So this is an example. If we take benchmark images, for example, from MNIST or CIFAR-10 datasets, the idea is that we have these small images, 28 by 28 pixels or 32 by 32 pixels, and then we are going to modify one pixel inside these images such that the corresponding classification is completely different. Like here we have a ship, and then by modifying this pixel, turning it into a blank pixel, let's say that it becomes a car. Or otherwise a horse is classified as a frog, a deer as an airplane, and so on and so forth. So the question is, how do we select this magic pixel for doing this one pixel attack? And the selection of the pixel is done in this work by Su and others using evolutionary algorithms. So just to give you, I think that okay, this was right. Okay, it is, sorry, I don't know what happened with this. We skipped a lot of slides just by clicking a single time. Okay, so here we are. We have this optimization problem that we want to solve. And basically what we want to do is to minimize the loss function between the, let's say, the adversarial example x prime and the corresponding output label L prime, such that the corresponding perturbation is smaller than a particular constant. In particular, this constant will be 1, because we want to modify just a single pixel. So the idea is that you are encoding your image inside a vector, and each component is a pixel of the image. And we are considering then the L0 distance here. So this is why we have the norm of eta with the subscript 0, which basically means the Hamming distance. There is a bit of, let's say, something to be precise here, because when you are considering the Hamming distance, so the thing where you say, okay, you have two vectors, x1, xn, and y1, yn. If you compute the Hamming distance, then what you are doing is to just say, okay, if these are different, for example, these coordinates, then I add 1. So I'm counting the number of coordinates that are mismatched. The problem is that this is a distance, but it is not induced by any norm. So calling it like a norm in that sense is not precise from the mathematical point of view. But again, in papers you see people talking about the Hamming norm. It is not a norm because you don't have the homogeneous property of norms, if I remember correctly, but you have everything else like triangle inequality, so you can use it as a pseudo-norm in a certain sense. But anyway, this was just, let's say, something about the notation to be aware of. Anyway, what we want to do is to say, okay, we have our image that is encoded by a vector where each component, each coordinate is a pixel, and then we are going to modify at most 1 pixel to craft our adversarial example. And the problem is that we could say, okay, let's say that we want to update a single pixel and select it by computing the gradient. So basically we have our loss function that is saying how far is, let's say, our pixel from being a good adversarial example that is able to mess up the classification. And then we want to follow this gradient and just do some gradient ascent. The problem is that this approach is not feasible because we have too many pixels to consider. So if we consider the Cypher10 dataset, the search space would be composed by what? By images that are 32 by 32 pixels. Each pixel is defined by 3 channels, red, green, and blue. And then we have 256 values for each possible channels. Notice that these are basically 32 by 32 are the dimensions of our vectors. So in total, we are dealing with something that is a vector that is, let's say, x1 up to x1024. So we are in the space R to the 1024, which is quite big. So basically, brute force is not possible here, and the solution is to use evolutionary algorithms. So just as a quick recap, if you remember, evolutionary algorithms are iterative optimization algorithms that we saw yesterday to design symmetric cryptographic algorithms or primitives. And the idea is that we start from a population of candidate solutions to our optimization problem, and we compute the cost function or the fitness function to see how good these candidate solutions are in solving our problem. Then we apply selections operator, crossover, mutation, and evaluate the fitness to compute the next generation. Then we do some replacement of the next generation with the old one, and we decide whether to terminate or go for another round of the evolutionary algorithm. In particular, what is used in the one pixel attack is an evolutionary algorithm that we didn't see yesterday that is called differential evolution. So if you remember, genetic algorithms are mostly for discrete space combinatorial optimization problems. And genetic programming, it can be used also for continuous problems, but mostly we've seen it in the discrete setting as well for Boolean functions. Here instead we are considering heuristic, an evolutionary algorithm that is specifically designed for continuous search space. So the idea is that if you take, let's say, the solutions, the candidate solutions in your search space, they will be inside the space R to the n, let's say. So they are defined as vectors, as real valued vectors. And then what we do in differential evolution is to pick for each possible point inside the population. So we will have a population that is more or less scattered throughout the search space R to the n. And for each of them, we do the following mutation procedure that is called adaptive mutation. So we pick 3 random vectors. So we have, let's say, our initial individual E that is part of the population. So it is, I, that will be, or let's call it X. That will be a member of R to the n. And then for each of them, we take 3 other individuals in the population. So A, B, and C inside pop. And then we create what? We create this new child, let's say, using the following formula. So it's D equal to A plus alpha and the difference of B minus C. So what is the idea? The idea is that we are constructing the new child, basically disregarding the original parent in a certain sense, this X here, because here we took something else from the population that was randomly chosen, and then we combined them using this particular formula. So here we are computing the vector sum of the first vector A plus the difference between B and C. So the idea is what? Well, there is also this factor here that is determining how strong is this difference, the contribution of this difference inside the creation of the child. So the idea is that if we have a population that is scattered a lot, it will be likely that B and C are far apart from each other. So here you will have something that is, let's say, a very high number. And what does it mean? It means that this mutation step basically will explore a lot inside the search space. So if we have a scattered population where all solutions are far apart from each other, then we have children that are very different also as well. So we are doing more exploration in the search space. On the other hand, if the population is converging towards a local optimum, then these will be closer to themselves. And it means that also the subsequent mutation will be smaller. And so we are not doing a lot of exploration there anymore. We are doing more exploitation. And the question now is, okay, I computed this child here, but now what do I do with the, let's say, original parent? Well, you can have, for example, crossover first between X and D. What is called I is X here on the blackboard, actually. So you can do crossover, but it is not necessary, and in particular in the one pixel attack, crossover is not used. But in the end, the selection comes in the moment where you create, let's say, these, so in this case of the one pixel attack, and looking at the slide, we will see that E, that was the, or let's say, the result of the crossover between I and D, here will be just D. So we are just taking the identity function. So this will be the final child, and then we compare the fitness of X with the fitness of the child E. If we are in this situation, so the fitness of E is strictly larger than the fitness of X, then we replace E with X. Otherwise, we keep X. So it's very greedy in this sense. And this is the selection mechanism for differential evolution. Okay, questions so far? Everything clear? Okay. So here is a visualization of how the one pixel attack works. So assume that we have one image that is composed just by 3 pixels. So it's very stupid, but it is just to have an idea of how it is working. Then we can, let's say, we can represent the space of all possible images as a 3-dimensional cube, because the cube will be given by, let's say, each direction is itself, let's say, a 3-dimensional vector where you have the coordinate R, G, and B, and then each of them can be a number between 0 and 255, because we are considering an 8-bit depth for our images. So an 8-bit intensity for each of the possible 3 colors. So we will have, let's say, a cube where each direction, each dimension is representing one of the 3 pixels. And then one specific point inside this cube will be a particular image, basically. So what does it mean to perform a one pixel attack? Well, basically it says, okay, I'm selecting a single pixel, either the pixel 1, pixel 2, or pixel 3, and then I'm moving the original image along the axis of this cube. Otherwise, if we are considering a 2-pixel attack, for example, we are moving over a plane in that case that is defined by the directions of the 2 pixels that we have chosen. In general, if we have something that has, like in the 1-pixel attack with cipher 10 images, we have 32 by 32 images, then we are considering again a cube that is with 1024 dimensions, so a hypercube with that particular number of dimensions. So the idea is that now we are going to, let's say, encode the array of our perturbations. So what we want to find is the perturbation, the optimal perturbation that is able to fool the classification of the neural network given a particular image. So the encoding will be something like this. It will be an array or a vector, let's say, of perturbations, and each perturbation is a vector of 5 components. So we will have the first component here, the first vector here of the perturbation that will be said, okay, we have the spatial coordinates of the pixel, x1, y1, and the values for the red, green, and blue. And this will be the first perturbation that we are applying. Then we can have many more. So we can have other perturbations, so another pixel, 2, G2, G2, and so on, depending on how many perturbations you want to apply. Basically, in the 1-pixel attack, you are considering a perturbation vector that is just composed by a single 5 tuple. And with this, we apply differential evolution, and then we try to optimize the fitness function that is measuring how good is this particular perturbation in fooling up the classification of the neural network. And these are examples, again, that you can have using this 1 pixel attack of applying, let's say, a single pixel perturbation with the found by the differential evolution. And yeah, so here I have, so far, do you have any questions on this? Or everything is clear? Yeah.
Just a little curiosity, because the point of using this type of techniques that perturbates directly the input, I guess it's mainly because from an adversary it's easy to perturbate the input, because probably there is a preliminary step in which there is the input submission, and after there is the, let's say, the black box of the model, which is applied and with all the terms. So maybe an adversarial is easy. It's easier to modify something which is before the black box model instead of modifying something that is within the black box model.
Yeah. So the fact is that maybe it is not even possible for the adversary to modify something inside the black box model, because, for example, you are in a setting of machine learning as a service, so you're querying some server, and you are definitely not seeing what is the neural network. So you can just submit your query and see what is the output of the classification.
Because many times there are, I see in which many works there is, let's say, they used to create embeddings based on the input. So basically, evolutionary neural network, for instance, the input is processed along the hidden layers, the convolutional layers, and then there is the feed-forward part, which there are, let's say, the input layer, the feed-forward, which is after the convolutional layers, which is basically the macro properties of the given input in some sense. So maybe if you perturbate something that is within the neural network, maybe it's easier to fool the prediction, but this is not going to be very easy, because you have to put yourself within the network.
Yeah, you need to have like a greater control of your of the neural network, or a greater knowledge.
So this is in practice. It's
not very realistic.
So I guess I don't know. I was wondering if in theory maybe there's some portal which is not practical, just theoretical, which adversarial crafting the result recommendation is within the network itself.
No, there are also some kind of attacks like that, but the idea is, at least as far as I know, we could also ask Stjepan actually tomorrow, because he knows more about these things. But for example, if you consider an hardware implementation of a neural network, like on a TPU or whatever, then you could have like a clone device. The adversary could have a clone device, and then over that he could try to do, for example, fault injections. So to introduce some errors inside the circuit of the neural network, and then again there it would be something like black box in a certain sense, because it doesn't know the whole specification of the networks, because there will be some hardware protections or some other kind of countermeasures that basically hampers the white box knowledge of the adversary. But it can try to modify directly the network during the inference time.
So there's adding an epsilon to some of the internal activations, for instance.
But for example, so there are also settings, real world settings, where you can have something more, let's say, something stronger than the black box setting. That's for sure. And okay, other questions? Everything quiet on the chat?
Yeah.
Good. Okay, then I think that we can also finish a bit earlier. So after this, at 2:30, we will start again with defenses from adversarial examples and then see how to use differential privacy to implement such kind of countermeasures. Okay, see you later.